Okay, so today we're going to just learn two things, right? The first thing will be we're going to show some examples where an example of a function that is Riemann integrable but not Lebesgue integrable. And then second thing, the Lebesgue dominated convergence theorem, yeah? Okay, so these two things, right? Just excuse me for a moment. Okay, so for this particular example, we're going to look at this integral for one, okay? Right, so this integral, if you remember from elementary calculus, the function for sine x over x is like this. Okay, it's something like a dampening function. So your sine x will give you the oscillations, and then you look at your x, right? Since your x is increasing, so the amplitude of the oscillation actually decreases as x increases, yeah? Right, and this one, from elementary calculus, you know that the limit when x tends to 0, your sine x will tend to 1, right? This is when you learn L'Hopital's rule, I think this is one of the examples that's given, yeah? Take limit of sine x over x. So that will be 0 over 0, yeah? So you can use L'Hopital's rule, okay? There's also some other ways to show that the sine x of x it tends to 1 as x tends to 0. The other way is to show that use the infinite series for your sine, right? So your sine x is, if you go by infinite series, it looks like this, and so on, right? So basically, then you simplify, you get 1 over x squared over these things, right? So these are all functions of x. So your leading term is 1. So when your x tends to 0, so all these will disappear. So you get 1. Okay. So there are so this from elementary calculus, right? Okay. Now this integral is equal to pi. Okay. And in fact, this y is equal to 2 times of, since it's symmetric, right? So it's basically equal to this, right? Okay, so this one we take it as there are ways to show that it's equal to pi. Okay. So anyway, this is Riemann integrable, and now we're going to show that it's actually not Lebesgue integrable. Yeah. Okay, this function is not Lebesgue integrable. So for simplicity, we are just going to consider from 0. Okay, the value of x will start from 0 and go to infinity. Yeah, because it's symmetric. Okay. All right, so let's look at the sketch. Let me clear that. Okay, so you have the function will go like this, then up, down, up, down, up, and so on, right? So the first thing is we find the zeros, right? Find the zeros of s x over x, right? Now, for simplicity's sake, I will consider the absolute, right? So once you consider the absolute, so this part will flip up, okay? So this will flip up. Oops. This will flip up, and so on, all right? So we don't consider these parts, right? Okay. Find the zeros of the absolute of this function. So basically, the zeros occur at these points, right? Okay. So this would be pi. Okay. Sine pi is 0, 2 pi, 3 pi, 4 pi, and so on, right? Okay. Right. So you find the zeros, right? So after that, you think of it like this. So then you look at the interval for which you have the all these intervals. Yeah, look at the interval here. Okay. Now, you can find that the absolute, right? So this part over this interval, this function is bounded by this constant. Okay. So this constant over here is 1. And you find that over pi and 2 pi is bounded by this function, another flat line, right? And over this interval bounded by this flat line, and this flat line, and this flat line, and so on, all right? So it's very simple. So now I know that my f, right? Sorry, this is absolute of f, okay? My absolute of f is actually bounded by the sum of rectangles, right? So rectangle 1, rectangle 2, rectangle 3, and so on. The size of the rectangle is pi times the height, right? Of the rectangle, right? So for example, the first rectangle here, the area of the rectangle will be pi. The second one is, then we need to know this height, right? We got to know this height. Okay? So how do you find the height? So the height is basically the maximum point, right, of this curve, okay? It's basically the peak, right? Right, over all these intervals, okay? So, so how do we find the peak? So basically this one is So the peak actually occurs at the middle, right? So this will be, you take the midpoint of pi and 2 pi, that will be 3 pi over 2. This will be 5 pi over 2, yeah, the midpoint. The maximum occurs at the midpoint, okay? Be 7 pi over 2, right? So the midpoint over here will be, you substitute, for example, this one, you will substitute sine of 3 pi over 2 over 3 pi over 2, right? So sine 3 pi over 2 will give you 1, right? Okay. This will give you 1. Sine 3 pi over 2, let's verify that it's actually 1. That is, so you take absolute, right? You're taking absolute, so it's equal to, so sine 3 pi over 2 is how much? Okay, it'll be minus 1. And then you take absolute, it becomes 1, right? So over here, so you know that so you know that all these values, sine, so this will be, the general term will be 2k plus 1 over 2, yeah, and over 2k plus 1 over 2 pi. All right, you can actually see this, right? So this is 3, so this is the odd term, right? 2k plus 1, the 2 is here, okay? So basically you substitute this into your sine, so you basically, the maximum is actually occurring at this, so the maximum value is actually this thing, right? So the maximum value corresponds to this in general. And this one is definitely bounded by 1 over 2k plus 1 over 2 pi. So this is 2k plus 1 pi, right? Okay. Now, okay, so that one is if you want to obtain a bound for your sine x over x. But this is actually, we don't actually want the upper bound. In this case, we actually want to have, because we are going to show that the integral is not exceeding, it is actually not existent. So instead of using the upper bound, we look for a lower bound, right? So let me clear this. Just a just a minute. I have a sinus problem here. Just bear with me. Okay, let's continue. Okay, just now we had this thing, right? Okay. Then you you consider absolute of f, which is this. Now, and we know that so this is pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on. And the maximum occurs at the midpoint, yeah? So that will be 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, and so on, okay? Now, we make this observation. Just now we can find an upper bound, but we can also find a lower bound, right? So in this case, the lower bound will be you use the triangle here. Okay. Okay. Actually, this doesn't really matter. You look at this triangles, right? So you know that if you take the integral of f, right? Okay. In this case, you will have to consider the positive part, right? And subtract the negative part. Okay. So, so we are just going to show that even for the positive part, right, it's already divergent. So in this case, let's sketch out the positive part. So your function is like this. So this is your f. So your positive part will be this. Okay, it's your f plus, and your negative part will be this. Should we left out something? Okay. So the positive part is here. Okay, and the negative part is here. Flat goes up, flat goes up. Okay. All right. Okay. So the positive parts will be, let's say here, right? So this will be the positive parts, and this will be the negative parts, right? Now we want to show that even so if you take the Lebesgue integral of absolute f. Basically, let's say we consider only the positive part, right? Which is these things, right? So they already have. So you look at this, right? So the Lebesgue integral of f plus d mu, it exceeds. All right. It already exceeds the sum of the rectangles, of the triangles, right, at this position. So this will be, this is pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on, right? So the rectangle over here between The rectangle between 2 pi and 3 pi, rectangle between 4 pi and 5 pi. Sorry. And so on, yeah. Okay, the size of the rectangle between 2 pi and 3 pi is what? 1/2 times the width, right? The width is always pi times and times the height. Okay, so the height is given by a sine of, in this case over here will be sine of 5 pi over 2 divided by 5 pi over 2, right? So that is going to give you, for the first one, it will be 2/5 pi. Okay. For the next one, the area of the triangle will be as usual, and over here is between 4 pi and 5 pi, so that will be 9 pi over 2. Okay. Right. So you can see the pattern here. So the pattern here will be you keep on going. So it will simplify. So this will be cancelled off, right? So basically, the you know that the integral of f plus d mu is definitely greater than or equals to 1/5, this guy, plus 1/7, this guy, and so on, plus 1/9. Okay. And we know that this sum, right, is actually infinite. Okay, this is the P series where P is equal to 1 in elementary calculus, right? When you try to find the sum of things like 1/n, n equals to 1 until infinity, raised to the power of p, yeah? P equals to 1, this series is divergent. Okay, which is basically saying that you are taking things like 1 plus 1/2 plus 1/3 plus 1/4. You keep on adding, this is divergent. All right, so this is this particular series is also divergent, yeah. Because basically this is also this part is something like 1/2 n plus 1. Doesn't matter, your n is starting from 2 and onwards, but still overall the power of the p is still 1, right? So this is actually a divergent series. Okay, so since your Lebesgue integral for f plus is already divergent, right? So when you have a divergent integral, this cannot, then that's it. This entire integral is divergent, right? You don't even have to care about this part. Okay, so so you either show that integral of the positive part is divergent or the integral of the negative part is divergent. Doesn't really matter. You can also show that the sum over here is also divergent. Okay. So in this case, you don't actually have a Lebesgue integral because of this particular situation, but the Riemann integral exists. Okay, this is just to point out to you that the definition of the Lebesgue integral will also cause some kind of pathologies. Okay, but it's not a major problem because we basically can switch back and forth between both integrals as and when is convenient. Okay. All right. So this is the example of a function that is not Lebesgue integrable. Before we move on, do you have questions? Okay, maybe you'll have questions later. Sorry, I'm not in very good form today, so maybe the explanation was a bit all over the place. Okay, you might probably have to reread the rewatch the video later for clarity. Okay, so I'm going to move on to the topic of dominated convergence. So, okay, let me just state this thing here. Okay, it states the following. If your absolute of Fn is bounded by some function g almost everywhere, and g is integrable, and Fn converges to F almost everywhere, then F and Fn are integrable, and integral of Fn d mu converges to integral of F d mu, right? Basically, this amounts to saying that the limit is equal to this. Okay, so this limit is F, right? So this is also your the interchange of limit and integration operation. But the previous one that you studied was you had to show uniform convergence of Fn. For this one, you just need to establish that your absolute of Fn is bounded by some function that does not depend on n. Okay, and you have these conditions like almost everywhere. Almost everywhere simply means here that like I gave an example on Tuesday, right? When you say Fn converges to F almost everywhere, it can be a situation like this. Like for example, let's say this is your F, right? So this is your F1, your F2, and so on, right? So in the limit, they kind of like converge, right? They become, your Fn converges to F, right? But you say almost everywhere, it means that, like, for example, over here, it may converge to for all these values except at, let's say, the 0 point here. Let's say it has, in the limit, for all values of x, your fn is actually f, but at x equals to 0, is actually equals to, at that point only, yeah? This is what we mean by almost everywhere. Because at this point, right, this point is a singleton. Okay? So a singleton has 0 measure, right? The measure of a single point is 0. So we don't care. As long as the convergence is to all possible values of x except at a set of x where you have 0 measure, we will say that it converges almost everywhere. All right. This is a kind of like a more relaxed criterion for convergence. If you say Fn converges to F everywhere, that means for this example, it will fail because this point here is actually not in the limit. Your F is equal to this constant, but at this point it's not. Okay. So when you say it's convergent almost everywhere, that means there is a set of points where the convergence does not happen, but you don't care about it because those points are countable and they have 0 measure, so they won't affect your integral if you are going to find the area under the curve of f, right? So this is where the almost everywhere comes out. And it's the same over here when you say that a function is bounded by another function almost everywhere. Like for example, I could have the function sine. Okay, so my sine function is like this. Okay, so let's say sine anyway, sine of nx over n. So that would be it would actually dampen. Let me see. We'll go like this. Okay. For n equals to 1. So go, if n equals to 2, so it will be smaller, yeah. And so on, okay? N equals to 3, it will be even smaller. Okay, so towards when n goes to infinity, basically it will converge to 0, right? Converges to 0. But let's say, right, if you define your, let's say, okay, probably this is not a good example because this is everywhere. It converges everywhere. So maybe not a good example. Maybe let me choose another example. So let's say we choose Fn equals to this. All right. So when your n is equal to 1, okay, when n equals to 2, you will still start from here, but it will decay faster. N equals to 3, n equals to 4, and so on, right? Okay, so it just keeps decaying faster and faster, but at x equals to 0, it's always 1, right? Okay, so in the limit, your Fn, right, is going to converge to 0 almost everywhere, okay? Because in the limit, all of this will become 0 except at this point, all right? Okay, so, okay, your absolute of Fn is bounded by 1. It's bounded by 1, definitely. But you could also find some other functions, such as, for example, you could find, let's say, Fn. So this is e of minus x over 2. So your Fn is definitely bounded by this. Okay. Almost everywhere. Well, over here you could specify a slightly pathological function here. Like for example, it goes like this, but at certain points, right? Let's say you can dig out certain points. Maybe it comes here. This one goes here. All right. Although you don't have to construct such pathological examples, but this is just for illustration. In practice, we would basically just use the continuous form, right? But let's say you choose to use some function like this by digging out holes at certain places, right? And you put a value that is maybe lower. You'll find that, of course, this red line here, this red curve will dominate, right? It will dominate your F1, F2, and so on at all places except maybe these points, right? Like in this point, it's not dominating, okay? Because your function is actually larger than these points, the height. But it doesn't matter because at these points, right, since they are singletons, the measure is actually 0, okay? So, so almost everywhere, requirement is actually a relaxing requirement, right? So as long as it occurs almost everywhere, except at certain points where you have 0 measure, then it's fine, right? You will be happy with that function. Okay, so this is the ingredient is first you have to find some kind of bound for it, right? And then after that, you can do your interchange. Okay. So we're going to look at one example here. Okay. The example just now. So we're going to just go until 0, 1. Okay. F1, yeah, F2, and F3, and so on, right? In this case, it's very simple. This is 1. Okay. Now, we want to find this integral. All right. So this is your Fn. And let's see how we use Lebesgue dominated convergence to justify the interchange of limit and integration. Now over here, your Fn, the absolute of it is still, it doesn't affect the function, the absolute, because it's positive. is bounded by 1. Okay? And 1, so your 1 plays the role of g. So 1 is integrable over 0, 1. All right, it has to be integrable over 0, 1. Okay? So therefore, you have domination, right? So you already established domination. Because of that, you can interchange, right? And this clearly is actually 0. So it's 0. Okay. In fact, if you do it follow the order of doing this integral, so you integrate this will get you this. Okay. So you end up with 1 over n, 1 minus this. All right. So if you take limit, so this will become 0, right? Because in the limit, this will be 0, and the denominator will be very large. So this will tend to 0. Okay. This is just an example to show this domination. Now, what if you wanted something like this? What if you wanted something like this? So you will have to find a dominating function that is integrable over x from 0 to infinity, right? So therefore you cannot use 1 anymore because you integrate 1 over this is actually, it's not integrable. Okay, so in this case you would find a natural choice would be something like what we showed just now, e of minus x over 2. Okay, so definitely your absolute of f is dominated by e of minus x over 2, and this does not depend on n, right? So, and this is definitely integrable over that, right? Integral of e minus x over 2 d mu, right? Over your 0 until infinity. So this is the Lebesgue integral, right? So basically, over here, this Lebesgue integral is the same as your Riemann integral. Right, and we know that this is definitely giving us some kind of finite amount, right? So because of this, we can justify the interchange. And this, of course, is again 0. Okay. All right. So the to use Lebesgue's dominated convergence theorem, the only important part, I think the most critical part is to find the dominating function, right? For this, it helps if you can sketch your Fn, and then from there you can get some ideas, right? What should the appropriate G be? Okay. Right. Okay. Let's take a break now, and when we come back, we will go through tutorial 3, and then I'll assign students to do tutorial 4. Okay, you can find tutorial 4 in Spectrum, and then I'll say something about the assignment 1. Right. So let's take a 10-minute break now. We'll come back at 12.
Okay. Can you hear me, doctor?
Yes.
Okay. For question 1, the question say that let F be a sigma field, and then we want to show that if A1 and A2 and so on is in F, then the intercept union of AK is in F, and for part B, the union intercept AK also in F. So I'm not sure whether I do it correctly. So for part A, we want to show the intercept union of AK is in F. We know that if A1, A2, and so on is in F, then the union of all the AI is in F. And then the same goes to the union of the AK. And then the intercept union of AK actually is equals to the union of all the A. So it's in F. And then for part B, the union intercept of AK for A1, A2, and so on is in F, then the complement of each of the A1, A2, and so on also in F. And then the union of all of this complement is in F. And the complement of all of the union of this complement, AI complement is in F. Actually, this equals to the intercept of the AI. So in the end, we know that the union of intercept of AK is actually equals to this and is in F.
Okay. So yes, I think it's correct.
It is correct. Like how I write the notations.
Yeah, I mean, so basically you work from the first principles, right?
Yeah.
Okay, you want to show that particular operation, right? You have some sets A1, A2 until so on. You want to show that that those operations that you applied, they create sets that still belong in F, right? So then the way to do is like your first one is you start, okay, so your A1, A2 until so on is in F, then by definition of F, the union is also in F, right? It's closed under countable union, right? So okay, so then it's closed under countable union, so that means it doesn't matter, right? It could be your I can start from 1, can start from 2, can start from anything, isn't it?
Yeah.
So that's why you have that it doesn't matter. So your union of A, K start from N. Your N can be anything, right?
Yes.
In F. And since it's an element in F, it's closed under countable intersection, right? Because your U of AK is in F. So therefore it's also there's closure under countable intersection, right? Yeah, that's why you have the last one. Last one is you basically closure under countable intersection. Okay.
Okay.
Second one is you have to use complementation. Yeah. So the second one is basically a slight extension where you start from A1, but then you use the closure under complementation, okay, to establish that the complements are in F. Then use countable closure under countable union of AI's the complement. So then you get that, right? Okay, that's correct.
Okay.
Okay, thanks.
Okay.
Yeah.
Okay. Thank you.
All right. Okay. So next question we have one more, Hakima. Is one here?
Okay. Can you see the screen?
Yes.
Okay. For problem 2, let omega is 1, 2, 3, 4, 5, 6. So we need to identify whether it is a fit. For those that are not, generate a sigma field. Okay, So for A, F naught is equal to empty set and 6 omega. So we can see here that this is a trivial fit. Then so for the first condition is omega is in fit, so it fulfill the condition. Second, for A is in fit, then the complement is also in fit, so it fulfill the condition also. And for A, B is in F, A union B is also in F, so it is a field. For B, we have empty set 1, 2, 3, 4, 5, 6, and omega. First condition, omega is in F, it's fulfill the condition. A is in F, A complement is in F, it also fulfill the condition. And for A, B in F, A union B in F also fulfill the condition. So it is a field. For C, F naught is 1, 2, 3, 4, 5, 6, 6, and omega. We can see here that the for first condition it fulfilled, but for the second condition, it's not fulfilled the condition, as for the omega, it doesn't have the empty set, and for 6, it doesn't have 1, 2, 3, 4, 5. So it's not a fit because property 2 is not satisfied. So we do a sigma fit here. So we add empty set 1, 3, 4, 5. Then we fulfill the second condition, which is A in F, then A complement is in F. And the third condition also fulfilled. So it is a sigma field.
Okay, you 6 doesn't have a complement, so you generate its complement, right?
Yes.
And then you put empty set inside. But then this is not yet it's not yet a sigma field, because if you look at 1, 2, 3 union 6, it's not inside.
Okay.
Yeah. So you have got to put in some extra things, because this is not actually a sigma field yet, because the sigma field has to be closed under countable union, right? But so you see 1, 2, 3 is in this set. 6 is also in this set, but their union is not in this set. Right? So it does not yet fulfill the definition. So you got to add one more. You go to add one more set there, which is 1, 2, 3, 6. Your sigma field generated by F naught, right? You got to add one more.
So add 1, 2, 3, 6.
Yeah, 1, 2, 3, 6. See, because 1, 2, 3, 6 is the union of 1, 2, 3, and 6. Right?
Oh, okay, I understand. 1, 2, 3, 6, 1, 2, 3, 6, and then
Yeah.
2.
I think that's all. You just need one extra 1, 2, 3, 6. The rest, I think 1, 2, 3. Yeah, if you this 1, 2, 3, 6, you can take union of with the other sets, but they will just lead to omega. So yeah, you just left out 1, 2, 3, 6. Okay, once you all these kind of things, yeah, once you have generated the sigma field, check that if you apply the operation of countable union on all the members in this set, they will produce members that are still in this set, right? So that's one way to check.
Okay.
Right. Okay. Thank you, Wano. The question 3 we have Aswari.
Yeah, I'm here, doctor.
Aswari. Oh, sorry, Aswarya.
Yeah, you just can call me Aish.
Aish. Okay.
Yeah. Can see my screen, doctor?
Yeah.
All right. So for problem 3, consider the sample space omega equals to 1, 2, 3, and A equals to the empty set and 1. A is a collection of subsets of omega. So for A, find the sigma field generated by A. So this is my sigma field generated by A. I just use the operation of complementation of 1 with respect to 1. So I just added 2 and 3. So this is my sigma field generated by A. And there are 3 properties to be checked to show that this is a sigma field generated by A, but I'm not sure if this is necessary to be shown.
No, you don't have to. You just no, you don't have to.
All right, so this is right.
Yeah.
All right, so moving on to B, suppose we construct the probability triple, omega, the sigma field generated by A, and the probability measure. What can you say about the probability of 1, 2, and 3? So we know that our sigma field generated by A is the empty set, consists of the empty set 1, 2, 3, and also the omega. So we can assign a probability measure to 1, that is the probability of 1, as 1 is in the sigma field generated by A. However, it is it is meaningless to talk about the probability of 2 and 3, as 2 and 3 are not in the sigma field generated by A.
Yeah, that's right. In order to assign a probability measure to some set of interests, that set must be in the sigma field that goes together with your probability triple. Yeah.
Yeah.
So this is just to reinforce this idea, right? Because if it's not in that sigma field, then you can't talk about it.
Yes.
Okay.
All right. So for C, give a proper construction of the probability triples such that it is meaningful to talk about the probability of 1, 2, and 3. So I let my sigma field generated by A star. This is like a new sigma field, which consists of the empty set 1, 2, 3, 1, 2, 1, 3, 2, 3, and the omega. So this is a sigma field. This is because you can see all the elements are closed under complementation and also countable unions. So I have this as my probability triple. So I say that this is the proper construction of the probability triple such that it is meaningful to talk about the probability of 1, 2, and 3 as this 1, 2, and 3 are in the sigma field of A star.
Yeah, that's right.
Right.
Yeah. So basically, for if your omega is discrete, right? You can always generate the power set as your sigma field. Your power set is definitely your sigma field.
Mm-hmm.
And once you do that, all the usual kinds of events that you're interested in can be is well defined already. So yeah, the usual way is to just for a discrete omega, just generate your power set, and then you can start talking about. That's why most of the time when you study elementary probability, right, you ask like, what's the probability of getting, for example, you can ask all kinds of probabilities like, what is the probability that you throw the coin? What this one is so 1, 2. Okay, so you can ask what's the probability of getting 1 or 2, right? So 1 or 2 that will correspond to the set 1, 2. Yeah. And 2 or 3, so that will correspond to set 2, 3. Okay, so yeah. Okay. Okay, thank you, Aish.
All right. Thank you, Doctor.
Okay, next question we have Shaswani.
Doctor, can you see my screen right now?
Yes.
Okay. So for problem 4, a football game can end in 3 outcomes: win, lose, or draw. A team will be playing 2 matches, so the question asks us to write down the sample space, then construct a sigma field such that it is meaningful to talk about the probability of getting 0, 1, or 2 draws. So from the question, we know that suppose a team will playing 2 matches, then the sample space is equal to win, 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 lose, win, draw, draw, win, DL, DD, LW, LL, and LD. And the total number of the sample space is equal to 9. So now we have to construct the sigma field. So for the sigma field, we know that the sigma field consists of all the subsets from the sample space. Thus, the field consists of the empty set, which is the smallest value. Then we would like to find the first element of set, which is WW, WL, WD, DW, DL, DD, LW, LL, and LD. And then we're also interested in a collection of subset consisting of 2 elements of set, which is WW, WL, WW, WD, WW, DW, and so on until LL and LD. This one, it consists of 36 sets, and we can find the third element set and until the I element of set, as long as we can assign a probability measure to each of them to the set of function of probability. So the question asks to talk about the probability of getting 0, 1, or 2 draws. So the probability of getting 0 draw is equal to probability of WW, WL, LW, LL, where we can see that this probability is element in the sigma field. And for the probability of 1 draw, the probability is equal to WD, DW, DL, and LD, where the probability also can see in the element of the sigma field. And lastly, for the 2 draw, the probability is equal to DD, where DD is element of the sigma field. I'm not sure, Doctor, am I doing the right things or not?
Yeah, you are doing it correctly. Yeah, so basically you just enumerated. I mean, like you just use your sigma field as the power set, which is actually quite large. You don't have to write down all of them, right? Because there will be 2 power of 9 elements, and that's actually a lot. You just need to explain like, okay, so it will consist of sets with 1 element. That's 9 choose 1. Then 2 elements, there'll be 9 choose 2, and so on and so forth, right? So yeah, so that set is actually quite large. And then just point out that the events that you want, right? 0 draw, 1 draw, 2 draws, they basically are just some kind of sets in your sigma field. And therefore, you can actually assign a probability measure to it. Okay? Yeah. So this is more like to give you something more concrete to hold on. Because in your first year, right, you will just, they skip all these things. They'll just say, oh, what's the probability of a draw? So then directly you will just go to say, oh, that will be that set, win, 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 lose, lose, win, lose, lose, right? And then you maybe have some assumption about independence. And maybe they'll just make further assumptions like winning is 1/3, losing 1/3, drawing 1/3. So then you can calculate that. But in order for this to hold, right, it all depends on that particular set being in the sigma field. And you don't have that problem in principle because you basically just construct your sigma field as the power set. Then all kinds of questions you can ask, right, about certain probabilities it will be that set will be inside your F. You can think of some other situations like what's the probability that you get what's the probability that you lose on the second match, right? So that will be what? Probability of losing on the second match. So that will be LL, WL, or LL, WL, or DL, right?
Yeah.
Yeah, and that set is actually inside your sigma field. That's why you can talk about it. Okay? So yeah, so it turns out that at the elementary level, since implicitly your sigma field is always constructed using the power set, therefore all kinds of those questions that come to your mind can be answered. Okay, so now you know it more clearly. Okay, thank you, Shazwani.
Thank you, Doctor.
Okay, the next one we have no Amira.
Yes. Okay.
Yeah, just share your screen.
Can you see my screen?
I can't. How about others?
Cannot.
Cannot, sekejap. Okay, wait. So sorry.
I think there's just a green button there. Share screen.
I cannot open it. Wait, can I ask my friend to share the screen for me? Wait a minute.
Yeah. Sometimes I don't know, like there could be some technical problems.
Yes.
Are you using a laptop or a handphone?
I'm using handphone because my laptop cannot connect to the internet.
Oh, okay. Yeah, sometimes the Android will have, I don't know, sometimes it might have some problems.
Okay.
In fact, it's possible to actually, if you're going to do a presentation and you might have a problem with your device, you can actually ask another participant to share the screen and then yeah, help you with it. Yeah, okay. Right.
Okay. So I will explain problem 5. The question asks, so let omega is the interval from 0 to 1 and consider the Borel sigma field of B. Find the Lebesgue measure or lambda of the set lambda intersection of interval x minus 1 over k to x. So what does this tell us about the Lebesgue measure of a singleton x subset of B? So first we find the interval of x minus 1 over k to x. So I plot the graph here where the interval is from k equals to 1 to k equals to n. So since it is intersection, we choose the smallest interval where I dot with the red pen here. So the intersection is equal to x minus 1 over n to x. So then we put the Lebesgue measure lambda into the interval. It seems that if we put the lambda into the interval, so the lambda of the interval is equal to 1 over n.
Okay.
Below. Okay. So then the question asks about the singleton x. So the limit, the singleton x is equal to the limit of the intersect of the interval. So then lambda of singleton x is equal to lambda of the intersection of the interval, where it is the limit of 1 over n. So it is equal to 0. So we can say that the Lebesgue measure lambda of the singleton x is defined and lambda singleton x is equal to 0. Okay.
Yeah, okay, good. Just a small thing, towards the end when you say so lambda of the singleton x is equal to the limit of that. Actually, it should be the The limit should go inside.
Oh?
You put the limit outside.
Oh, so I put the limit.
Yeah, because your
Oh.
limit of intersection of that is actually a kind of, that's a countable intersection. So you are putting a Lebesgue measure on the countable intersection. Okay.
Okay.
So the Lebesgue measure on the countable intersection is that, then the second row is okay lah. It's
Okay.
just to make the notation more coherent. Okay.
Okay.
Okay. So the takeaway from here is that if you have singletons, the Lebesgue measure is 0, and this is a fact that you can use later. Yeah. So therefore you have a countable set, right? Therefore the Lebesgue measure of a countable set is 0 as well, because your countable set is made up of countable unions of disjoint singletons, right? When you place a Lebesgue measure on that, it's basically just sum of the Lebesgue measure of the singletons. Okay, and since each of them are 0, so it's basically just summing 0, a bunch of zeros, right? So from here we know 2 basic facts already. Lebesgue measure of a singleton is 0, and the Lebesgue measure of a countable set is also 0. Okay, thank you, Amira. Okay, so now we go to, okay, let's look at tutorial 4. Okay, so tutorial 4, let me share my screen. Okay, can you see my screen? Can you see my screen?
Yes, doctor.
Okay, so tutorial 4, you have basically it's all on the Lebesgue integral, and also the use of the Lebesgue DCT, yeah, dominated convergence, right? So are there any students who want to try these questions? Just let me know. Okay, Fadila wants to try question 1. Farah, question 3. Nur Amir, question 2. The question 4, from what we learned today, actually question 4 is actually quite easy to do. You just need to find a dominating function for the integrand there. If you look at it carefully, you should be able to find it quite easily. You just need to do some careful observation, and you just need to find the absolute. Then you ask yourself, the absolute of this is bounded by what function? And that should be not very hard. Any takers? Question 4. Just try a good opportunity to learn. Okay, good. Najiha will try question 4. Question 5 is kind of like similar, but some help is given to you in the form of a hint, right? In fact, this now you start to see the connection to some of the mathematical statistics things that you learn. The integrand there is actually the I didn't say it there, but that integrand there is actually the probability density function of the T distribution with n degrees of freedom. So basically, this question is interesting. It's saying that if the degree of freedom is sufficiently large, then this is the CD. This is the distribution function. Yeah, the distribution function of the T distribution is equal to the distribution function of the standard normal distribution. So that's why when the degree of freedom is large, your T distribution is basically your normal. We can establish this fact by using the Lebesgue dominated convergence. So anyone wants to try this? There's one part that may be difficult, which I already kind of like give you the because that involves the gamma function. So that one is a little bit. It's not. We just need to know that it's equal to some constant, right? We're not going to go through how to actually get that because it's actually quite involved. If you're interested, you can actually look at some material on your own on limits of gamma functions. Okay. Anyone wants to try question 5? So you just need to find a dominating function for the function there. For this, I will just suggest to you that you sketch out some curves, right, for the T distribution. From there, you will get some ideas. It always helps to do sketches of the functions sometimes when you are dealing with sequence of functions, yeah, because you want to study their behavior. Anyone? No one? Okay, no one, then I have to just find someone who has not presented before. Let me see. Eric Tang. Is Eric Tang here? Eric? Eric Tang, are you here? Silence. Who else here has not presented? Let me me see. Have you presented before? Common limb. Common limb. Common limb, are you here? Not yet. Okay. So you do question 5, yeah? Try it. Okay, great. So this is for next week, yeah? So then I want to talk about the, let me see. I want to talk about, okay, continuous assessment 1, right? Okay. So this is your continuous assessment 1 take home assignment. So you can try this. If you want to discuss with your friends and all that, you just go ahead. You want to form study groups. You want to discuss it. Yeah, just go ahead, right? Because the whole point is an assignment, and if you can learn things from here with discussion, then all the best, all the better. Okay, just don't copy, right? Because if you copy, then you're not learning anything. Okay, you can try to form groups and then share with each other what are your thoughts about certain things. Okay, it's entirely up to you, right? How you want to do it solo, you want to do it by group, form groups and discuss. I leave it to you. So there are actually and let me see, there are 8 questions here. So the marks are given indicated for each question. So they cover all the material until tutorial 3. All right. Okay. So you have first problem on using epsilon definition of convergence. Then you have mappings and inverse mappings, limit supremum, uniform convergence, something on that. Some basic things about field and sigma field. Sigma field generated by a collection of subsets, and some similar materials that we just covered today. Yeah, Lebesgue measure. Okay, so overall not a complicated assignment. Okay, so for this you will make the submission on Tuesday. All right. So you have about 5 days to do it, and the submission is before 5 o'clock on next Tuesday, right? And you can actually just write it out and then scan your write down the solutions on paper, then scan and submit as a PDF. Okay. All right. So handwrite your solution, scan and submit as a PDF. Okay.
Okay, Doctor.
You do not have to copy. I noticed that some students will copy the questions. You don't have to copy the questions. Just write down the solution. 1 is what, 2 is what, 3 is what, and so on. Okay. All right. Okay. Yeah. So that's all for today. All right. Okay. So please make sure you sign the attendance.
Thank you so much, Doctor.
Okay. Thank you, everyone. So you check the video recording later, yeah. Okay, I'm going to end the meeting now. Okay, goodbye.
Thank you, Doctor.